Welcome back, everyone. Today we're going to talk about standard deviation and how it can be used to describe a data set. Now, in the past couple weeks, we've talked about mean, median, mode, range, box and whisker plots, stem and leaf plots, and all of that may have been old information from you, stuff you've seen prior in your math career, but I think standard deviation is going to be something that's entirely new to you. So I want to take a moment to explain what standard deviation is so that you can better understand what's happening when you do the calculation for it. In the past couple weeks, we've talked about measures of center, mean, median, and mode. We also threw range in there, but they were all measures of center. So in this skewed drawing here where we have a most popular option there, the median ends up being right here, and because of these outliers over here, the mean is drawn over to the left. We can see that each one of these could be considered the middle of the data in some way, shape, or form. Standard deviation is a measure of spread, so how far out the data is spread from a middle. Okay, so we've actually done a little bit of this. We've done some box and whisker plots where we can see where most of the data is concentrated and how far spread out to each edge it is. And we actually calculated a couple numbers to go along with spread, meaning like IQR, how big is one of those quartiles, how big are two of those quartiles, and how big is the whole thing from end to end, how far does it span. Well, now we're going to calculate a very specific number, and it on a perfectly symmetric set of data, the standard deviation is this much. And tomorrow I'm going to talk about exactly why it's 34.1% and so on. But basically we're going to go find the middle data. So this is the left of middle and this is the right of middle. And we're going to figure out how large that distance is. And we're going to interpret to see what it means as we can describe a data set with a single number, just like we could with mean, median, mode. We can now describe the spread of data with a single number, and we call this number today standard deviation. So the most immediate questions are, what is standard deviation and what can it tell us about a data set? Well, standard deviation, I'm trying to use the least number of words here. It's kind of a complicated idea, but standard deviation is the average distance any data point from the set is from the mean. So if you choose any point from random in that data set, it is likely to be X distance away from the mean, the calculated mean that we've done in the past couple lessons. Now, if you know that distance, there's a lot of things that it can tell you. Okay, so what if I know that the average point in the data set is, say, 5 units away from center, what can that tell us about the data set overall? Well, the biggest, most important thing, it is a measure of spread. So if we have a big standard deviation, that means the data is spread out a lot. It can start talking about probability. So the stuff in the middle is more common. So if we can identify where the middle is, we know that those outcomes or those data points are more common. We can also figure out what percentage in some cases of the data lies between two specific data points. We can talk about probability a little bit. We can also talk about whether something is so rare that it is considered an outlier. And we can also kind of quantify how rare something is by how far outside of one standard deviation a data point is. So you may have noticed this is a little bit more high-level interpretation based on a single number, and the calculation that goes along with it is also slightly more high caliber. It takes a little bit more to do. I'll just run through a quick example. This is not exactly the calculation that's done, but this is an illustration of how standard deviation works. So say I got that data set right there with 5 items in it. We can draw a number line and we can put those 5 numbers on that data set. And standard deviation is the average distance from the mean. So we need to calculate the mean. If you add up all those 5 numbers, divide by 5, you get a mean of 9. If we throw that on the number line 2, now we can measure the distance between all 5 data points and the mean. So if I go between 8 and 9, the distance is 1. If I go between 7 and 9, the distance is 2. And if I do that for all 5 points, I get those distances right there. Now what standard deviation is we take all those distances that are in blue, 1, 2, 3, 2, and 4, we add those up together, and we divide by how many items there were in the data set, roughly, and we get a number, and it says 2.4. So that 2.4, this is not the exact calculation for standard deviation, but it's the concept, it's the idea that most of the points are within 2.4 units of the mean. So if we interpret that, that means that if I draw a bar out that's 2.4 units this way and 2.4 units that way, that means that most of the data should fall within that range. And you'll notice that 3 out of the 5 points do that. So on average, a point chosen from our data set is 2.4 units away from the mean of 9. Most of the data falls within that range, 2.4 to the left and 2.4 to the right, and points outside of that range are pretty rare. Only 2 out of the 5 do that. And 2.4 tells us how spread out the data is. So if I did that calculation and I got like 1.2, that would mean that all this data is actually more scrunched up, centered on the mean, rather than a little bit more spread out as we see here. The next picture I want to show you is something called a normal curve. A normal curve is a curve that expresses, like, say you have a really big data set, and this is a representation. Think of it like a histogram with a whole bunch of different bins that are reaching a whole bunch of different heights here, and most of our data is over here, and data over here is less and less common. So what we're doing when we calculate a standard deviation is we're actually figuring out, like, if the standard deviation was 2.5 here, we know that there's a lot of the data between 2.5 to the left and 2.5 to the right. So the stuff in the middle is more common, the stuff out to the edges is less common. Now, our goal when interpreting a data set is that we want to get away from this visual and be able to look at just the number, the standard deviation, and maybe the mean, and be able to say something about that data set just by looking at two numbers. So again, the idea of a standard deviation is to be able to describe a data set with a single number rather than having to look at the entire thing. So let's learn some new symbols, and that'll help us speak a little bit more intelligently about the topic here. So the first one that you need to know is the standard deviation of a data set can be symbolized with the symbol sigma. This is a lowercase sigma. It's basically an O with a little tail sticking off the side of it. Now in this video I will eventually teach you how to calculate the standard deviation, but for right now we just want to know that this lowercase sigma stands for standard deviation. The next new symbol I want you to know about is X bar. X bar is just a shorter way to say average or mean. So within a formula you might see this X bar pop up, and that just stands for the average of the data set, just like we calculated a couple weeks ago. We're going to let X, now you've used X before, but we're going to let X stand for any particular specific item in the data set. So when you see X, that just means that we're choosing one thing out of the data set. The next one is a capital sigma, and it's much different than its lowercase counterpart, but it is also pronounced sigma. This is the capital version of it. It's a letter in the Greek alphabet. And what sigma, capital sigma, stands for, it kind of stands for the words add everything up that follows this symbol. So down here I have a little example right here. It says sigma x. That means add up all the individual data items in the data set. So just by expressing those two symbols, I've been able to say all of those two words. So you can see how this is shortening the amount of stuff that we need to write. The last symbol I need you to know is N. We've used N for a lot of things, and it's going to stand for the number of items in a data set. So for instance, in that data set we just had, it had 5 items, so N equals 5 in this case. Hopefully now, knowing these two symbols, we can look at a data set or just look at those two symbols and be able to tell something about a data set without actually looking at the data set. So suppose you're a high school track coach and have to choose between 2 runners to put on the roster for an upcoming meet. Both of your runners are seniors, so you've been collecting data on them and you know a lot about them. You crunch the numbers and you find that runner A has an average time of 57 seconds for the 400 meters, and he has a standard deviation of 6 seconds. Runner B has an average time of 55 seconds, but has a sigma, or a standard deviation, of 2 seconds. Which one would you rather put on the roster, and why? Well, I'm going to go back visual again, and I'm going to bring out those little normal curves there. And at the middle of a normal curve, you always put the average. So the average speed for each runner, one is 57 and one is 55. And you might say, well, let's just go with runner B because he's clearly faster. He's faster on average. But if you also take into account the standard deviation, we're able to see what the probability is of him running a faster or slower race. So if we go out one standard deviation, so if I add the standard deviation to 57, so I add 6 plus 57 and subtract 6 from 57, I can get a range of times that this athlete will typically run. Most common times he will run between 51 seconds and 63 seconds. Now that's really quite slow compared to his average, but that's a lot faster compared to his average. Now if you do the same thing with runner B, he'll most commonly run between 53 and 57. So the safe bet is to go with runner B because he's very consistently below 57 seconds. But if you want to take a chance and maybe give the guy a little rabbit or something like that, runner A has a higher probability of running a much faster race than runner B. So if you want to take that shot, there's a reasonably high likelihood that runner A will run faster than B. So here's my conclusion that I typed out. Runner B is more consistent and consistently faster than runner A, but runner A has a pretty strong likelihood of running faster than runner B just because this his sigma is, or his standard deviation is much larger. His times are more spread out than runner B. So he has the capacity to run faster than runner B in more cases. So with this little example, you can see how deep we can make conclusions about two different data sets just by knowing two little numbers. So let's actually go calculate these numbers. Now, how do you actually calculate standard deviation? So there's the formula, and I wish I could just give you the formula and let you go at it, but I'm betting that you have a couple questions on how the heck you actually evaluate that. And believe it or not, we're actually not going to use the formula. I just wanted to show you the formula because it looked cool. I'm going to give you a table, okay, and a process by which to follow. We're going to do this formula, but we're going to break it down into little steps, okay? So remember that our job is to find the average distance of each data point from the mean. So the first thing we're going to have to do is we're going to have to find the mean. So add up all the numbers, divide by how many there are, get your mean. Then you're going to find the difference between every single data point and the mean. So you're going to do, like, you know, if your data set has 10 items in it, you're going to take each of those 10 items and subtract the mean from them. Once you have those differences, you're going to square each difference. The reason for that is because some of those differences are going to be negative, and we always want to talk about a distance as being positive. So we're going to square each one. Then we're going to add up all those differences that we just squared. So we're going to have some pretty big numbers, and we're going to add them all together. So you can see right here, there's where the sigma comes in. It says add up all the individual items minus the mean and that distance squared, and you're going to add all those up. The next thing in the formula is to divide it by the number of items. It's actually the number of items with the exception of one. So if you have a data set that's 10 items, you want to actually divide by 9 here instead of 10. So that's a little bit weird, but we're going to do that. And then finally there's a square root, and that basically undoes the squaring operation. We made all the numbers too big, so now we're going to bring them back to normal by taking that square root. All right, so time to take a breath here. And let's do an example, okay? So on your worksheet today, you're going to have a table like this. And if you're doing this video with notes out, yeah, take the time to draw out a table here. We have 8 different data points, so we have 8 rows here by 3. And we're going to walk through this data table, and we're just going to fill in it as we go. So here we go. The first thing we want to do, first step was to find the mean. So if I add up all those 8 numbers and divide by 8, I get an average value of 5. And I also noted that the number of items in the data set was 8. So those are two very simple, quick things that we can do. The next simple, quick thing that we can do is we can put all of our numbers into this first column here. Our next job is to take each of these numbers and subtract the mean from it. So I go 5 minus the mean, which is also 5, and I'll get 0. 5 minus 5 is 0. 5 minus 5 is 0. 6 minus 5 would be 1. And I can do that all the way down that column there. You'll notice that some of the numbers get negative. The next column over is I just take all those numbers and square them. So 0 squared is 0, 1 squared is 1, 3 squared is 9, and you can see all the numbers are now positive, but they're also bigger than what the actual distance is between a point and the mean. So we're going to add all these numbers up, do that. Then we're going to divide it by n minus 1. So n minus 1, n is 8, so we're going to divide by 7 here, and I'll get a pretty nasty decimal. And then I'm going to take the square root of that. So that brings those large numbers back to a normal size again. So our sigma is 1.512, which means that most of the points are within 1.512 units of 5. And that's a standard deviation calculation. You have to do that a couple times on the homework. Before we go, I want to do one more problem, this time with 6 units, and you may have noticed that was a kind of an easy example because most of the numbers were integers. This one is a little bit more difficult, so if you want to pause the video, make yourself a table again, go ahead and do that. If we go for the low-hanging fruit first, I'm going to go calculate the mean of this as my first step. I'll note how many numbers are in it. It looks like there's 6 this time, so if I add them all up, divide by 6, I get 6.5. So my average, my x bar, is 6.5 this time. So now when I do this subtraction, I'm going to get a decimal each time. But just power through, do that subtraction, you get these numbers, and then we're going to square each one of those numbers. Now when you square a decimal, you get an even bigger, well, a longer decimal, I'll say, and also a bigger number. Now we got to add all those up. Now notice how many opportunities you have to make a typo on your calculator if you're doing this by hand. So be careful as you do this. Add all those numbers up. You'll get 65.5. We're going to divide it by n minus 1. This time there were 6 items, so we're going to divide by 5. So we get 13.1, and then our last step is to take a square root of that number, and we will get 3.619. So that means that all the data, or most of the data, was within 3.6 units of 6.5. All right, your assignment for today is to complete the Stats 6 worksheet, and Schoology will ask you for your response to number 5.